Scientists were supposed to be finished with 3I Atlas by now. The interstellar visitor arrived, lit up headlines, broke a few models, divided astronomers into camps, and then started drifting back toward the dark. On paper, that's where the story ends. You publish the papers, do the interviews, and move on to the next object. Except that's not what's happening. Because if you look at what astronomers are actually doing right now, the real telescope schedules, the late-night coordination emails, the observing logs 3I Atlas is still being watched. Not casually. Not as a footnote. As a priority target, telescopes that could be pointed anywhere are still tracking a fading speck that should already be boring. Teams that should have moved on are still burning precious nights staring at something most people think is old news. And that raises a simple but uncomfortable question. Why are scientists still watching 3I Atlas this week? What are they afraid of missing? Because once you understand what they're actually measuring right now, you'll realize the most important part of this object's story may not be what it already did, but what it hasn't done yet. A comet, even a strange one, follows a familiar arc. It enters the inner solar system from the cold, dark outskirts. As it warms up, ice begins to sublimate. Gas jets erupt. Dust lifts off the surface and spreads into a glowing coma and tail. The object brightens as it approaches the Sunday. That's the dramatic phase, the one that fills social media feeds and telescope galleries. Then it passes perihelion, its closest point to the sun, and everything starts shutting down. The sunlight weakens, the energy drops. Jets quiet, the coma collapses. Brightness fades along a smooth, predictable curve that astronomers have been using for decades. After that, the science becomes routine. You confirm the fade matches the model, publish the final plots, and eventually the object becomes too faint to justify time on large telescopes. The story ends with a graph, not a cliffhanger. That is exactly what should be happening with 3I Atlas right now. But when astronomers plot the latest data, real photometric measurements from different observatories, different filters, different instruments, something refuses to line up. The points don't fall where they should. There's no dramatic flare. No obvious explosion, nothing easy to explain away. Instead, night after night, the brightness sits just slightly above where the model says it should be. Not enough to make headlines, not enough to dismiss as noise, just enough to be irritating. The inner coma still looks sharper than expected. Tiny bumps appear in the light curve when images are stacked together. Different telescopes see the same pattern. And this week matters because the curve is reaching a decision point. Either the brightness finally bends downward and the object behaves like a normal fading comet, or it keeps stalling, proving that whatever is powering it isn't done yet. That's the first reason scientists haven't walked away. They're trying to catch the exact moment when 3I Atlas reveals what kind of object it really is. Brightness alone would already be enough to keep astronomers interested. But that isn't the part that really locked their attention. From very early observations, scientists noticed that 3I Atlas didn't just glow, it pulsed. Its brightness rose and fell in a repeating pattern. At first glance, that sounds normal. Comets rotate. One side heats up, another cools down. Light curves wobble all the time. If the nucleus is an uneven lump tumbling through space, you expect a regular rhythm, one bright side, one dark side, repeating like a slow lighthouse. But when researchers looked closely at the data, that isn't what they saw. Instead of one clean peak per rotation, the light curve showed multiple peaks, layered on top of each other. A dominant rise, followed by smaller pulses, then another rise. Not chaotic, but not simple either. The pattern looked less like a spinning rock and more like several active regions taking turns. One patch of the surface vents strongly brightness spikes. As it rotates away, another region swings into sunlight, another spike. Then another. The result is a light curve with a kind of internal rhythm, as if different parts of the object are firing independently. That alone would be interesting. But then something else happened. When astronomers tried to line up the data from multiple nights, folding the light curves over a single rotation period, the peaks refused to stay aligned. Each night, they arrived slightly earlier than expected, then earlier again. The only way to make the data fit was to shorten the rotation period. That means the object wasn't just rotating, it was spinning up. Jets weren't merely releasing gas, they were applying torque tiny off-center thrusts, acting like uneven thrusters. Over time, those thrusts were changing the spin state of the nucleus itself, and that's dangerous. 3I Atlas isn't a solid rock. It's a fragile, porous body made of ice, dust, and fractures. Spin it too fast and centrifugal forces start pulling it apart. Cracks widen, material sheds. In extreme cases, the object can fragment completely. So now scientists face a very specific question, and it can only be answered right now. Has the spin stabilized? If this week's light curves line up cleanly with last week's rotation period, that suggests the torque has eased. The jets may be calming, internal stress might be leveling off, but if the period continues to drift even slightly, it means the forces twisting this object are still active, and structural failure remains on the table. That's why astronomers are burning entire nights tracking a fading speck. Because if 3I Atlas does break apart later, everyone will look back at this week and ask one thing. Did the light curve warn us? If brightness and rotation were the only problems, scientists might still be arguing quietly in conference rooms. But dust is where this story stops behaving like an ordinary comet. In a normal comet, dust follows simple rules. Small grains get pushed hard by sunlight and form the classic glowing tail that stretches away from the sundae. Larger grains lag behind, drifting along the comet's orbit and slowly spreading into a faint trail. Radiation pressure, gravity, and gas flow sort everything out in predictable ways. 3I Atlas didn't follow that script. At one point, it developed a structure pointing roughly toward the sun, what's often called an anti-tail. Normally, that's explained away as a geometric trick. If Earth happens to cross the plane of a comet's orbit, the dust trail can line up with our line of sight and briefly appear to point the wrong way. Perspective illusion. Case closed. Except this time, the physics didn't cooperate. When researchers modeled the dust in detail, they found the grains responsible weren't tiny, fluffy particles. They were large, around 10 microns across, much bigger than typical interstellar dust. That size matters. Grains that big are heavy enough to resist being blown away by sunlight, meaning they can hold together in a sunward-pointing structure, but they're also heavy enough that lifting them off the surface requires strong, sustained gas flow. In other words, the comet wasn't just shedding dust randomly. It was producing exactly the kind of grains needed to build this structure. Then came the part that made people deeply uncomfortable. When scientists estimated how many of these grains were packed into the cloud, they found the dust veil had an optical depth close to 1. That's a critical threshold, thick enough to block direct views of what's behind it, thin enough to scatter light instead of going black. It's the precise balance you'd expect if you wanted to hide detail without announcing that you're hiding it. You can call that an extraordinary coincidence of natural processes. Or you can admit why people started whispering. Because whether it's natural or not, the consequence is the same. This dust environment isn't passive, it's structured, and as 3I Atlas moves outward, those dust streams don't vanish. They stretch, twist, and integrate into the solar system itself. That's why astronomers are still stacking deep exposures this week. They're watching the architecture evolve in real time. Is the anti-tail fading? Is it thinning? Is it breaking into filaments? Does the inner dust veil become asymmetric as activity shifts? These late-stage observations matter because you never get a second chance at this phase. Once the nucleus drops below detection limits, the dust is all that's left, and that debris may cross planetary orbits for centuries. If Earth ever passes through that stream, this week's data will be the map. And that leads directly to the next problem scientists can't ignore. Brightness, rotation, dust, all of that would already justify continued attention. But there's another reason scientists simply cannot stop watching 3I Atlas, and it's buried in the math of its motion. On paper, this object should be easy. An interstellar visitor arrives on a hyperbolic trajectory, gets gently bent by the sun's gravity, maybe nudged slightly by the planets, and then leaves on a clean outbound path. Newtonian mechanics handles this beautifully. You write the equations once, fit the data, and the future positions fall neatly into place. That's not what happened. From early on, astronomers realized they couldn't match observations unless they added something extra, a non-gravitational acceleration term. In plain terms, 3I Atlas wasn't just being pulled by gravity, it was pushing itself. Gas, jets, and outgassing were acting like tiny thrusters, subtly steering the object off the path gravity alone would predict. At first, that wasn't alarming. Plenty of comets need small corrections like this near perihelion. The problem is that the corrections didn't stop. As weeks passed, orbit solutions kept needing updates. New astrometry came in, and suddenly yesterday's trajectory was slightly wrong. NASA issued revised ephemerides. Uncertainty bars widened instead of shrinking. The object passed Earth safely, far away. There was never any danger, but the fact that its path kept refusing to settle told a deeper story. Whatever was driving the acceleration wasn't a brief surface flare. It was persistent. That's why astrometric teams are still measuring 3I Atlas down to fractions of an arcsecond this week. They're feeding fresh positions into orbit solvers and asking a very precise question. How much extra push does the object still need? If the latest data fits with a smaller, non-gravitational term than last week, that suggests the jets are finally calming down. The object is relaxing into passive flight. If the term stays the same or worse, grows then 3I Atlas is still actively altering its own trajectory. And that distinction matters more than it sounds. In a natural scenario, sustained outbound thrust implies a structure capable of channeling volatiles from deep inside, not just surface frost, fractured layers, internal reservoirs, possibly even a hollow geometry that keeps feeding activity long after sunlight weakens. In a technological scenario, the one nobody says out loud in official papers, it implies something else entirely. A system capable of controlled, prolonged thrust without obvious fuel exhaustion. Either way, the data refuses to collapse into a comfortable category. And this week is a narrow window. Too early, and the behavior looks like noise. Too late, and the object becomes too faint to track accurately. Right now is when the equations decide whether 3I Atlas is settling down or continuing to push. That's why the orbit still has everyone's attention. But there's one final layer, quieter, less visible, that keeps scientists listening long after the light fades. There's one part of this story almost no one hears about unless they dig through technical reports and observing logs. Not light, not dust, silence. Throughout this entire encounter, radio observatories have been quietly listening to 3I Atlas. Arrays like Green Bank and other large dishes have pointed at the object, scanning for narrowband radio signals, the kind that, in most contexts, don't come from rocks. These aren't casual checks. They're long integrations, carefully tuned searches looking for anything that stands out from cosmic background noise. So far, they've heard nothing. On the surface, that seems reassuring. Silence supports the just a comet interpretation. If it were something artificial, wouldn't it transmit? Wouldn't it announce itself? Not necessarily. If 3I Atlas were a derelict probe, it could be dead, drifting, unpowered, mute. If it were an autonomous system designed to observe without being noticed, silence would be a feature, not a failure. You don't spy on a neighborhood by turning on a loudspeaker. And more mundanely, it could be communicating in ways we aren't listening for, or only in short bursts outside our observation windows. That's why silence doesn't close the case. What it does is tighten constraints. Every additional hour of listening this week lets scientists say something very specific. If there is a transmitter on or near this object, it must be weaker than this power level. At these frequencies, with this duty cycle, those limits matter. Null results are still data. Weak limits are still limits. That's why, even as optical observations become harder, some teams are still sneaking in radio time. Because if anything were to change, a structural failure, a sudden release of energy, a final burst triggered by stress, you'd only catch it if you were still listening. And then there's the uncomfortable pattern this object fits into. We like to number interstellar visitors as isolated events. First was Oumuamua, tiny, dark, accelerating without a clear coma. Second was Borisov, more familiar, but chemically strange. Third is 3I Atlas, combining the most troubling aspects of both sustained activity, unusual dust, changing spin, self-steering motion. One anomaly is easy to dismiss. Two are interesting. Three starts to look like a trend. That's when a new branch of astronomy quietly forms. Interstellar object science. And right now, 3I Atlas is the laboratory. This week's observations aren't just about this object. They're training data. Practice for 4I, 5I, 6I. Astronomers are learning how fast they need to respond, which signals matter early, which anomalies deserve immediate attention, and when an object crosses the line from curiosity to mission-worthy. If humanity ever intercepts an interstellar visitor with a spacecraft, the playbook will be written from cases like this, from the faint, frustrating, late-time data that most people never see. That's the real reason scientists are still watching 3I Atlas this week. They're not waiting for a dramatic explosion. They're watching for the quiet clues. Because when this object finally slips below the noise floor for good, the question won't be, what did it do? It will be, what did we almost miss? This is where the story stops being about one object. We like to treat interstellar visitors as isolated flukes. One weird rock shows up, does something strange, and leaves. Case closed. But when you line them up, that comforting idea starts to fall apart. First came Oumuamua, tiny, dark, no obvious coma. Yet it accelerated as it left the sun, as if something were pushing it gently from within. No dust. No gas signature strong enough to explain the force. Scientists proposed exotic explanations: hydrogen ice, nitrogen ice, fractal dust, even solar radiation pressure acting on an ultra-thin structure. Then came Borisov, more familiar on the surface. A classic-looking comet with gas and dust, but chemically wrong. Its composition didn't match anything we'd seen from our own solar system. It looked natural, yet clearly formed somewhere very different. Now comes 3I Atlas, and it combines the most uncomfortable features of both. A small nucleus acting like a large one. Sustained activity that refuses to fade. Rotation that speeds up instead of settling. Dust structured in ways that strain coincidence. A trajectory that keeps needing extra push. One anomaly is easy to dismiss. 2 are interesting. 3 is a population. And that's when a new field quietly forms. Interstellar object science. 3I Atlas isn't just being studied for its own sake. It's being used to define what normal even means for visitors from other star systems. Every late-time measurement feeds directly into how astronomers will handle 4I, 5I, and whatever comes next. How fast do we need to classify them? Which signals matter early? What combination of brightness, spin, dust, and trajectory says this one is different? This week's data doesn't exist in isolation. It's rehearsal, training, stress testing our models against a real object that refuses to behave. And that leads to the final reason scientists still won't look away. There are hundreds of comets in our solar system. If you miss one, another will come along in a few years. You don't get that luxury with interstellar visitors. So far, in all of human history, we've seen 3. One arrived before we knew how to look. One came while we were still building the tools. This one arrived when we were finally paying attention. That's why astronomers are still tracking a fading dot this week. Not because they expect fireworks, but because they're afraid of missing the quiet transition, the moment where a comet stabilizes, adapts, or fails. If 3I Atlas fragments later, people will come back to this data and ask whether the warning signs were there. If it fades smoothly, this week defines the boundary of normal behavior. If it keeps pushing, spinning, and shedding in subtle ways, then our models change again. And if someday humanity launches a spacecraft to intercept an interstellar object, the decisions that mission makes, where to aim, what to measure, how fast to respond, will be shaped by what we learned right now. This isn't the end of a story. It's the drafting of a playbook. So why are scientists still watching 3I Atlas this week? Not because they expect a dramatic final act. Not because they're hoping for a last-minute surprise. They're watching because this is the only phase you never get back. They're watching for the small deviations, the quiet drifts, the subtle clues that tell you whether this is a comet dying, a comet adapting, or something that was never quite a comet to begin with. As the world moves on, there are still people on mountaintops and in control rooms lining up faint guide stars and telling their software, track that dot again. Because until 3I Atlas finally slips below the noise floor of our instruments, it has one job left. To teach us what interstellar space really sends our way. And we have one job in return, to keep listening. If you want to follow whatever this week's data reveals, whether it's another bump in the light curve or the quiet moment when the signal finally disappears, make sure you're subscribed. Drop a like so this reaches more people. And tell me in the comments, if you had one last night on a big telescope with 3I Atlas, what would you measure? Because the visitor may be leaving, but the lesson is just beginning.